Let us talk about this problem. We are given a string. We need to find lexicographic rank of the given string. Let's understand lexicographic rank using pen and paper method. Let's say the given string is BAC. To find the lexicographic rank of BAC using pen and paper, what we do is we first sort all the characters of BAC, so we get ABC. Now we generate all permutations of these three characters in increasing order, in lexicographically increasing order. So first permutation ABC, second is ACB, third is BAC, BCA, CAB and CBA. And all these permutations are written here in lexicographically increasing order. Now we see is where does this string BAC fit in? So BAC is at the position number 3. That's why BAC's lexicographic rank is 3. Let's see the next input, CBA. CBA comes at the last position among all the permutations. So lexicographic rank of CBA is 6. Now DCBA. If you see DCBA, it contains 4 characters and there are factorial 4 permutations, 24 permutations, and DCBA is going to be the last string in these permutations, right? So lexicographic rank of DCBA is 24. Now what will be the lexicographic rank of ABCD? It's going to be 1, right? Among all the 24 permutations, ABCD is going to be at the first position. Now we'll shortly see how do we get the number 598 for a string. The method is same. You sort the characters, right? You put G first and then I and then next increasing character, then generate all the permutations of these characters, then see where does this string comes in at what position. That position is actually 598. Now please pause this video and think of an approach that takes a string as an argument and returns an integer value which is lexicographic rank of the string. Let us first talk about a naive solution to solve the solution. A naive solution is simply to follow this pen and paper method. We generate all the permutations of a given string in increasing order. While generating the permutations in increasing order, we compare the permutations with the given string, and if any permutation matches with the given string, we return the count of permutations that we have generated so far plus 1, or we just keep on incrementing the count, right? So that's one way of finding lexicographic rank of a string. Now what will be the time complexity of the solution? See, there are going to be factorial n permutations for a string of length n, and you are going to compare every permutation with a given string. So in the worst case, like this string, when your given string is last in the all permutations, in the worst case you will generate all factorial n permutations and you will compare every permutation with a given string, and given string length is n. So you are going to take n into factorial n time at least in the worst case. That's the worst case time complexity of this naive solution. We have a solution that works in linear time. Now please pause this video and think of a solution that finds lexicographic rank of a string in linear time. Let us first talk about the idea for the efficient solution with this example. Let's say we have this example string. So the main idea is to count smaller strings, count lexicographically smaller strings and add 1 to it. That's your result, right? If you know how many strings are lexicographically smaller than this and you add 1 to it, you get the rank of this string. Now how do we count lexicographically smaller strings than given string? For that purpose, we traverse through string from left to right, and for every character what we do is we see how many characters are smaller than this on the right side, right? Because if we replace that character from those smaller characters on the right side, we will get a lexicographically smaller string, right? So we begin with character S. How many characters on right of S are smaller than this? 4 characters, R, I and G. So if I replace S with any of these 4 characters, I will get a lexicographically smaller string. How many lexicographically smaller strings I will get if I put the first character as R? 1, 2, 3, 4, 5, factorial 5 strings. Similarly, if I replace S with I, I'll get factorial 5 more strings. So the count of lexicographically smaller strings that do not contain S as a first character is 4 into factorial 5. 4 characters are smaller and 5 places are to be filled with remaining 5 characters. So this is about the first character. Now we have counted all the lexicographically smaller strings that do not contain S as a first character. Let us now count all those lexicographically smaller strings that contain S as a first character. For that, we can't now move S. Now we go to the second character and we repeat the same process. We count how many characters on right of T are smaller than T, and we again get 4. So we can replace T with 4 characters, and then we can have factorial 4 permutations for every character, because we have 4 places left after it. There are total 6 characters in the string. So we have 4 in place of T. If I put in place of T 4 smaller characters, I'll get these 4 different prefixes, and for every prefix I will have factorial 4 strings. So I have 4 into factorial 4. So now I have counted all the strings that begin with S but do not begin with T. Now I am going to count the strings that begin with S and T. So these are the strings that begin with S and T. Now we have the third character R, and we count how many characters on right of it are smaller than this, right? So right of R, we have 3 characters, all 3 are smaller. So we have 3 into factorial 3. We can replace R with I, with N, with G, and then we can have 3 factorial 3 permutations. So this is the count we get when we replace R with smaller characters. Now we fix the next character. We fix the character R, and we count how many characters are smaller than our next to R character, which is I, right? Because if I replace I with smaller characters, then only I'll get lexicographically smaller strings, and my task is to count lexicographically smaller strings. So I can replace I with G. There is 1 character. That's why we have 1 into factorial 2. We replace I with G, and then we have factorial 2 permutations, right? So 1 into factorial 2. Now we go to the next character in the same way. Next character is N. And how many characters are smaller than N? Only 1 character, G. Smaller than N on right of N, right? Right of N is important because previous characters we have already counted, right? We have counted strings that don't begin with S, strings that begin with S but don't begin with this, right? So we only need to count on the right side. On right of N, we have 1 character, and this is smaller. So we can replace N with G, but we have only 1 place left to be filled. So we have 1 into 1 factorial 1 permutations that we get with this setup. So these are all counts of lexicographically smaller strings, right? And if I add these count, I get 597. So 597 strings are lexicographically smaller than this. Then what will be the rank of the string? It will be 597 plus 1, right? Count of lexicographically smaller strings plus 1. So we use this idea to count lexicographically smaller strings, 597 strings, and then we add 1 to it. So our result is going to be 597 plus 1, which is 598. Now you have enough idea how do we get the lexicographic rank of this string. Please pause this video and try to implement this approach in big O of n time. Let us now see one more example to get better idea of the problem. We have say string DCBA. We know this rank is 24. Now how do we get 24 using this method? We process all the characters from left to right. For D, we count how many strings are smaller than this. For that, we count how many characters on right of D are smaller, right? So there are 3 characters, A, B, C. We can replace D with all these 3 characters, and we get 3 into factorial 3 permutations of strings which are smaller than DCBA and do not contain D as a first character, right? Now we need to count these strings which are smaller than DCBA and contain DCBA as a first character. So these remaining are those strings. Now we fix D, and then we check for C, same process. How many characters on right of C are smaller than C? 2 characters. So we put 2, then we have factorial 2 permutations for everything. So 2 into factorial 2. Now for B, we have 1 character smaller A and factorial 1 permutation plus 1 into factorial 1, which is 1. So we get 3 into 618 plus 4 plus 1, 23. These many strings is smaller, plus 1 is equal to the rank of this DCBA. 23 strings are smaller than this, so its rank is 23 plus 1, 24. Let us now see implementation of the efficient approach. In this implementation, we are assuming that all characters of our input string are distinct. However, you can easily extend this solution with duplicate allowed strings as well. So if you remember the solution that we just discussed, the idea was to traverse the string from left to right. Say this is the string, we traverse it from left to right. For character S, we count how many characters on right of it are smaller than this. So we saw 4 characters, then we multiplied 4 with factorial 5. Right? When we came to T, we counted how many characters on right of it is smaller. There are 4 characters. We multiplied this 4 with factorial 4. So we need a factorial value in every iteration. In the first iteration, we need factorial 5. In the next iteration, we need factorial 4. In the next to next iteration, we need factorial 3, then factorial 2, then factorial 1. For that purpose, what I have done here is I have pre-computed factorial. So I have not written code for factorial. I assume that you all can write the factorial code. So there is one factorial function that I have already computed. I have computed factorial 6, pre-computed it for the string. Now inside this loop, if you see, I am dividing factorial, pre-computed factorial by n minus I. So in the first iteration, I'll divide it by 6, right? So I'll get factorial 5 and I need factorial 5. In the next iteration, I'll divide it by 5. So I'll get factorial 4, right? So I'm dividing by n minus I, n minus 0, which means n minus 1, which means n minus 1, right? So first divide by 6, then 5, then 4, and so on. So this is how we get the factorial in big O of one time. Now, how do we get count of smaller strings on the right side in big O of one time? To get the counts of smallest characters on the right side, what we do is we use a count array. We initialize a count array with all zeros. This is C++ initialization with all zeros. In Java, it's by default initialized as 0, so we don't need an explicit initialization. After initialization, we count frequency of every character. And I said I'm assuming that all characters are distinct, so frequency will be at most once. At most 1, right? So we have 1 for G, 1 for I, 1 for N, 1 for R, S, T, right? So this is our count array after this first for loop. After we have computed the count array, we compute cumulative count for every index, right? So index I means sum of all the counts from 0 to I minus 1. And to do that, we do count I equal to count I minus 1 plus count I. Why are we doing all this? The purpose is to get counts of smaller characters on right side in big O of one time. We'll shortly see how does this help in getting this count. So now for every character, I have counts of smaller characters than it in the whole string. For example, if you see T, I can get the counts of smaller characters than T in the whole string as 5. I just need to go to index T minus 1, which means S, and I get the count as 5. There are total 5 characters smaller than T in the whole string. There are total 4 characters smaller than S in the whole string. So I can easily get this count. Now you must be wondering, like, this tells me the overall smaller character count. How do I get the count of characters on the right side? So the trick that we here use is we traverse the string from left to right. And when we have processed a character, we remove it from the count array. So when we come to a character, we have already removed the left character. So whatever we have is count of smaller characters on the right side only. So what we do is we begin with S, right? And we first compute like how many characters are smaller than this. We get it using stri minus 1. In Java, str.char at I minus 1. We get counts of smaller characters, we multiply it with the multiplier that we just discussed, right? Which is, for example, 5 here for the string. After doing this, we update the count array. And to update the count array, we use this character as an index. We go to the right side of it and reduce every value by 1, right? Similarly here, we go to the right side of here and reduce every value by 1. That's the simple idea. So you process the characters from left to right. You update the count array, you reduce their counts on the right side so that when you come to a character, you have already removed the left side characters. Let us now see implementation step by step. So after first loop, we have counts. After second loop, we have cumulative counts. So this tells me how many characters are smaller than or equal to n. And just index before tells me how many characters smaller than this. So just before for n, this value will be 2. For m, it will be 2, right? For n, it becomes 3. So first thing we are doing is factorial 6. 6 characters are there, we compute factorial 6. Now we run a loop, right? We have cumulative counts, we have factorial, we have computed everything. Now we come here. We run the loop for I equal to 0. We update our multiplier variable, which stores the current factorial. We divide it by 6, we get 120. So we are processing the character S when we are here at I equal to 0. So we got the multiplier as 120. Now we get how many characters are smaller than this character S. For that we just go to the previous index R, we get the count as 4. So we multiply this count with multiplier 120. So we get 4 into 120. So we get this value 480 plus 1, 481. So we get the value 481. Now we go to the next index T, and when we go to the next index T, we update the multiplier by dividing it by 5. So we get 24. And one more thing, when we processed S, we reduced the counts of all the characters on all the indexes on right side of it. So we reduced this count by 1, so we got it 5, and we also reduced this by 1, so we got it 4, right? And we reduced it to 5. Everything basically, this is last index, so we are not going to use it, but everything was reduced by 1. So this was happened after you processed S. Now we have come to T. So when you come to T, you first update the multiplier, right? Now you add 481 previous result plus count of str T minus 1. So T minus 1 is 4, right? So you got the count of smaller characters on the right side because you reduced the count when you processed S. So we have 4 into 24 equal to 577. Now we update the counts of characters on right side of T. So you get the multiplier. Your multiplier is 2 now. Earlier it was 6. So you get the count as 595 plus 2 equal to 597. Now you move to the next character. And before you move to the next character, you update in values on the right of this character. So this character was I, right? At I equal to 3 we have I. So for I and on right side of it, we are going to reduce the values by 1. So it's going to become 1, it's going to become 2, it's going to become 2, it's going to become 2, 2, 2 and 2. Now we go to the next character n. When we go to the next character n, we count how many characters are smaller than this. So on the left of n, you must be having a value 1, right? So you get the value 1 and your multiplier must have been reduced by divided by 2 now, so it must becomes 1 now. So now your 597 plus 1 into 1, you get 598. And you run loop till n minus 1 only, because for this character there won't be anything on the right side, right? So there won't be anything smaller. So we get the final result as 598, which is our lexicographic rank of the string. Now talking about the time complexity, this is constant work. Assuming that character size is constant, so we create a constant size array, it's a constant work. This is big O of n work, right? We are processing through the string. This is again a constant work, and this is big O of n work. Although we have a loop inside it, but it's a constant loop, right? So n into constant is a n loop, right? So we have n work, constant work, n work. So we and overall our time complexity becomes big O of n. If we want to be more precise, if we want to include the characters also as part of the time complexity, then we can write the time complexity as big O of char to create this array and initialize it, then plus big O of n for this, plus big O of char again. So I'll ignore this. Okay, let me write it. Char plus n into char, right? N into char. We can ignore these because these are lower order characters, and we can say the time complexity is n into char. And if char is a constant, then we can say it's a linear time complexity. And auxiliary space requirement is big O of char. So we have talked about a linear time solution for the problem, which is a great tricky solution.